So let us look at how the amide structure can be explained based on this different orbital approach. So here this is the structure of the amide. The nitrogen is having the sp2 hybridization as we have seen in the previous slide. The carbonyl oxygen bond, because carbon oxygen have a double bond, one of them is a sigma bond, another one is a pi bond. Pi bonds are basically formed by the p orbital overlap, and here again the lone pair on nitrogen is on the p orbital. So that means we have nitrogen lone pair in p orbital, the carbonyl pi bond is also there. So these two p orbitals are now in the same plane. So now the overlap or the resonance is possible in this particular structure. So instead of sp3 hybridization for this nitrogen in ammonia, what actually can be used is sp2 type hybridization with the lone pair is on the p orbital. That can be used to explain the structure in amide. So let us take another example of pyridine. So here in this particular case, pyridine is a 6-membered nitrogen heterocycle. So here the nitrogen is sp2 hybridized. Unlike the amide, here the lone pair of nitrogen is on the nitrogen's sp2 hybridized orbital. The unhybridized pz orbital is actually having one electron only. This electron is actually involved in the pi ring formation, that is the aromatic structure of this pyridine ring involves one electron in the pz orbital of nitrogen. So this is involved in the pi bonding or the aromatic ring of this particular pyridine structure. So here is the sp2 hybridized orbitals on the nitrogen. One of the lone pair is in the sp2 hybridized orbital, and the single electron is on the p orbital. Now if you compare between the amide and the pyridine, you have actually two different approaches. In the amide nitrogen, the lone pair is on the pz orbital, but in the case of pyridine, the lone pair is in the sp2 orbital. So which is actually the correct one? This doubt many of you may have. So how do we explain these strange phenomena of nitrogen having two different types of hybridized orbitals? So the students ask the question, sir, I am confused. For these nitrogen compounds, actually where is the lone pair? Is it in the pz orbital or sp2 hybridized orbital? I am confused. The answer is it actually depends. See, let me explain how to identify where the electron will be. The stability of the resulting species will decide where the lone pair of electron is going to be. If we take the amide, we need the lone pair in the pz orbital for effective conjugation. In pyridine, if you put the lone pair in the pz orbital, that is, you put the lone pair of electrons on the pz orbitals, you will have 8 electrons in the pyridine rings pz orbitals. So if there are 6 electrons, then we have the aromatic system which is very stable. So in the case of pyridine, we actually put the lone pair on the sp2 hybridized orbital and not on the pz orbital. Moreover, pyridine is basic. In other words, the lone pair is freely available. So that means it is not involved in the resonance. So the better way to put the nitrogen's lone pair is on the sp2 hybridized orbitals, which is very easily available. On the other hand, if you look at the pyrrole, which is a 5-membered heterocycle, the nitrogen lone pair is involved in the resonance. My question now, can you tell me where will you put the lone pair?
On pyrrole.
Let me draw the structure of pyrrole. So in this structure, this is pyrrole, we have pyridine. So both are having nitrogen with lone pair. So where we will put, whether we will put the lone pair on sp2 or pz orbital. In the case of pyridine, we put the lone pair on sp2 hybridized orbital and one electron in this pz orbital. Because here we have 5 carbons, 1, 2, 3, 4 and 5. All of them are having 1 electron in the pz orbital. Nitrogen is also having 1 electron in the pz orbital. So, if you put together, there are 6 electrons in the pz orbital, which leads to 6 pi electrons. According to Huckel's rule, this is the most stable one. So, in the case of pyridine, we have to put the this single electron on the pz orbital for aromaticity. But if we take the pyrrole, we have 2 pi bonds. So, there are total 4 pi electrons. There is 2 electrons, that is the lone pair electron on the nitrogen. This also should be on the pz orbital. So, when this is in the pz orbital, we have 4 electron in the p orbitals. So, total 4 plus 2 equal to 6 pi electrons will be there. So, this 6 pi electron again leads to aromaticity. So, in the case of pyrrole, we put the lone pair on the pz orbital, and in the case of pyridine, we put 1 electron only in the pz orbital. So, the stability of the final species, that is the aromatic nature, between pyrrole and pyridine decides where we will put the electrons. So, both are having basically, the nitrogen is having sp2 hybridization, and in pyridine the lone pair is in the sp2 hybridized orbital, and in the case of pyrrole the lone pair is in the pz orbital. By using this, we can actually explain the basicity of pyridine. And if you look at the pyrrole is not basic because the lone pair is not freely available. It is actually involved in the aromatic pi electron formation. So, the pyrrole is less basic. So, the observed phenomena of aromaticity and the basicity can be explained if we use the sp2 type hybridization for nitrogen. So, this is how we can actually explain not the sp3 hybridization, but sp2 type hybridization is responsible for the structure of nitrogen. So, let us recap what we have studied so far. The nitrogen in ammonia is not having the sp3 hybridization, but similar to sp2. The lone pair of electron on nitrogen is in the unhybridized p orbitals if nitrogen has 3 single bonds, say for example like ammonia, pyrrole, amide, etc. The lone pair of electron on nitrogen is in the sp2 orbital if nitrogen has 1 double bond, example pyridine, imine.